last class we discussed orbital elements, right? Now, one of the things I told you was you cannot really measure these orbital elements. You cannot go there and measure the orbital elements like the angles, the true anomaly, or for example the semi-major axis, the eccentricity. So what do you do? How do you get there? We'll take a look at something called, so the textbook identifies them as state vectors. Okay. This is chapter 4, section 4.4. So it talks about orbital elements and state vectors. And when they say state vector, they're talking about R and V. Okay. These can be measured, right? The R, the position and velocity of a orbiting body can be measured. It's very similar to, if you're trying to speed, cops can measure your position and velocity, right? It's very similar to that. You just shoot a radar, and you can measure the position and velocity. So the time of flight, you can use the time of flight, and using these two, we can arrive at the orbital elements. Okay. So we'll take a look how we can do that. The first, we're going to discuss, it's algorithm 4.2, but we'll discuss essentially orbital elements from R and V, determining orbital elements from R and V. This is, so first step is to calculate distance. Okay. Distance would be R, which is equal to root of R dotted with R. Just know that this is, what is the distance between this R and this R or this R? What is the distance between this? These are not the same R. One's a vector, one's a scalar, but you should know this is the distance and this is the position vector, the position of the orbiting body. The second step is again calculate speed. Speed would be V is equal to again square root of V dotted with V dot V. And this is again Vx square plus Vy square plus Vz square. The third step is calculate the radial velocity. Okay. So radial velocity Vr is equal to R dotted with V or R. Okay. This is equal to x bx plus y vy plus d bc. Then you calculate specific angular momentum. H equal to R cos V to all right, let's take a look at what we are doing here, okay? Now, will be something like this. You are given R and V, okay, in the ECI frame. What is the ECI frame? Let me pull up the figure again. All right. So if you look at this one, you see the ECI frame, right? We discussed this last class. Which is the ECI frame here? ECI or the geocentric equatorial frame? You forgot already? Earth. Right. So which is that frame over here? So you see this X, Y, Z. That is the coordinate system. That is the coordinate frame. That is the ECI frame. It is Earth-centered inertial. It's Earth-centered, right? Because it's at the center of Earth, and it's inertial. Geocentric is the same thing, right? Geo means Earth. Geocentric equatorial frame. It's called equatorial frame because the plane it makes, the X and Y axis make is the equatorial plane. Okay. Now, when we say we know R and V, we are essentially saying we know R and V in the ECI frame. How would you know R and V? Just think about this practically. If you have, if your orbiting body is here, you would shoot a radar in that direction, right? So you would know the distance, and based on your instrument, you know which direction that is, and you can trace that back to the ECI frame. You essentially know what longitude, what latitude you're in, and you can transfer between geocentric equatorial frame to geocentric right accession declination frame. Am I making sense? No? Lost? So again, you know this R and V in, let me put this here, in the ECI frame. Okay. So that is the reason see this IJK you see? It is this IJK. This is, IJK essentially is, I is X, J is Y, and K is Z. Okay. So this I or R is this distance. Okay. And it has an X component which is in the X direction or I direction, a Y component which is in the Y direction or J direction, and a Z component which is in the Z direction or the K direction. Got it? Similarly, your velocity will also have Vx, Vy, Vz. What do you mean by radial velocity? What are the two components of velocity here? See, this velocity, there is whenever you look at think about this. You tie a weight and rotate this. Okay, you just rotate a string with the weight attached at one end. This is the position vector, right? This distance is the position. See, if you're rotating it like this, so you're the reference frame. What is the velocity component of this? Huh? It doesn't have any velocity component? It does have velocity components. There are two velocity components here. One is tangential, which is this component. Okay. The other is this radial. So these two combine to give you this velocity component. This is the total velocity component which is in that direction. See, if it was only this direction, this would go out. If it was only this direction, it would just go straight line. Okay? So it tries to go in a straight line and this tries to pull it. That's the reason you have a radial component and a tangential component. And the effective, effective is what? It has to be this, right? This is a resultant. So that is that resultant in the same direction. Okay? So your velocity will always have two components, radial and tangential. And that is what you're seeing out here. The first thing we do is we calculate distance. Distance is just the square root of dot product. It is a scalar, correct? There's nothing special about this. Similarly, the speed is a scalar component. The radial component is r dotted with v. Why are we doing r dotted with v over r? Does this make sense? Projection. So this is a projection of vector r on vector v. Okay. So this is the radial component. We'll come to why this is important. Now the first, what we do is this is the definition of your angular momentum, h, right? So h, specific angular momentum. It's fairly simple. It is r cross v. So we use, these two are given. So we use this to calculate h and calculate the magnitude of specific angular momentum. Okay. The textbook will tell you this is the first orbital element. What did we say is our first orbital element? Recall what are the orbital elements we discussed, okay? First one was A, which is semi-major axis. Second is E, which is eccentricity. And then you have I, omega. This gives you orientation. Right? And finally you have theta, which is true anomaly. So we are going to calculate one at a time. We'll go first by what the textbook says, and I'll tell you how you can get A from. All right. So this is the first element. All right. H and you see HZ. Whereas if you resolve this vector in the ECI frame, the H vector in the ECI frame, it will have a component in X direction, Y direction, and Z direction. I is defined as the angle between this Z and this H, right? So if you look at what is cosine of I, what is cosine of I? So we have this. So this is your HZ, or it is Z direction, okay? And this is your H direction. This is I. So cosine of I is what? Right. It is, you can say Z over H, or you can say H of Z. It is, the angle is the same. If you get that component, it doesn't matter which one you use. You can say HZ over H, right? You can do that, right? So what we have done is we have just used that formula here. I is equal to cosine inverse of HZ over H. Okay. Now the next element. So this is the second element. Now, can you tell me what this N is? Anybody? Huh? What is this N? If you tell me what this N is and justify, you'll get you can get a lot of extra credit. See, your guessing is you won't go anywhere. Huh? Right. So what is that? Huh? You cannot guess. It is up there. Huh? See, this is what will make you an orbital space engineer. If you tell me what this N is, I won't bother you for the rest of the semester. Huh? No, it's not X. This N is actually this vector, the line of node. This vector. See, what you can look at N is, see this direction, right? You have Z crossed K is Z direction, okay? Z crossed with H. See, Z is always X crossed with Y, right? So you see, N is Z crossed with H. line of nodes? So that direction is actually this direction. Okay. You had your chance, Antoine. Yeah, I cannot make it any clearer than this. See, in fact, when I learned, I did not have this representation. We had to really visualize everything. So you guys are at an advantage. So this, you should be able to tell me that this direction, this is n direction. Okay. So think about it. It's just, so what we do is, I taught you this, right? X, Y, Z. So you have the Z is X. Okay. This is Y, and you have n coming down. Okay, this is an n vector. So why do we need this n vector? Why did we calculate this n vector? This angle is between n and this vector and x or I, right? So if you again take cosine of cap omega, you're going to get cosine of cap omega is what? So you have the 8th step is calculate magnitude of n. So it is n is root of n dotted with n, which is equal to, that's about it. So your cosine or omega is cosine inverse nx over n. Okay. So again, cosine inverse is something like this. You have, this is x direction, okay? And this is your n direction. If you resolve that n in again x, y, and z, this would be your nx component, right? And you're looking at this angle. This angle is what? Cap omega. So cosine of this angle is this n over this nx. Or, sorry, this. So you have nx, ny. The nz component is what? Nz. Do you see a nz component here? Nz is 0 because n is in the xy plane, right? So there is no nz component. Okay. So this is cosine inverse of cap omega is nx over n. Okay. Now the it's this angle. So you have to remember something about omega. Omega is cosine inverse nx over n. Y greater than or equal to 0. That is minus cosine inverse all right. I'll give you one extra credit problem which will carry a lot of weightage. Okay. I want you to implement a MATLAB algorithm which will, if you're given R and V, it will output the orbital elements. Orbital elements. Okay. So the extra credit, this is MATLAB exercise. Okay. Huh? You guys are going to give me trouble. Huh? You guys are going to really be in trouble. No extra credit. I think you need to learn. All right, the next. I gave you the orbital elements here. Okay. And see, this is what happens if you don't come on time. This was very discussed in very much detail. All of these last class. Entire class was spent on discussing the orbital elements. On Monday. So you should be aware of how many orbital elements are there. Okay. So that's it's really inexcusable if you ask me how many orbital elements are there. The next one is E. Okay. E is 1 over mu V crossed all right. So this is recall you can look back into your notes. Derivation of orbit equation. If you go back and look at the orbit equation derivation, you see this definition for E. Okay? And we use this definition. So why did we use this definition now? Because, see, we know mu because we know the central body. We know V, we know H, we know R and this R. So we can calculate E, right? And once you know this is the eccentricity vector, keep in mind. So how do you calculate eccentricity itself? E would be root of E dotted with E. Okay. This is step number 11. On this board you had two orbital elements. This is your third. Orbital element. This is your fourth. The next one is what is the eccentricity vector? Which direction is the eccentricity vector here? I told you guys last class. Eccentricity vector is always in this E is the eccentricity vector. It is in the periapsis or perigee direction. Okay? So if you look at this figure, this is that eccentricity vector. The perigee direction is the eccentricity vector. Okay? Now, do you see the angle omega? Angle omega is between N and E, right? That is how it is defined. It is defined as this angle. Okay? So again, how do we calculate? We just use the cosine law again, cosine inverse of. Now, this is slightly different from what you have seen. What is different here? Why couldn't we use something like this? Does this make sense, first of all? No? So what is N dotted with E? What is the dot product formula? N dotted with E is equal to what? Magnitude of N, right? Magnitude of E into cosine of angle between vector N and vector E, right? And this angle is what? This angle is omega, sorry, small omega, right? So this is N E omega. Therefore, omega is N dotted with E over NE. Cosine inverse I. Make sense? Okay. So this is your orbital element number 5. The next one is, what is the next one? Final one? It's true anomaly. Right? Again, you have to remember something. Omega is equal to cosine inverse N dotted with E over NE. E Z is greater than or equal to 0. And 360 minus cosine inverse N dotted with E over NE or EZ less than 0. And the final one is theta is equal to cosine inverse theta is cosine inverse So coming back to the extra credit, you're going to get 2% of your entire score if you just implement this algorithm in MATLAB. 2% overall grade. So it's and if I see any duplication, you lose 2%. If I see any duplication, any sharing of work, you lose 2%. Yeah. So that is a challenge. And you have to implement all of this as well, okay? 13 steps, yes. So if let's say if I give you just the R and V, if you use your program input R and V, it will tell me what the orbital elements are. Given R and V, you implement an algorithm which will output the orbital elements. Yeah, based on. So one of the things I would like to stress here is, see, we said what are the orbital elements we identified? All these are in here, okay? E, I, small omega, cap omega, and theta. But A, in this algorithm, we use H, right? So how do we convert H? How do we convert H to A? So you have H square over mu is equal to P, which is equal to A into 1 minus E square. Okay? So you can use this to convert between H and A. H is generally not regarded as an orbital element. So A is the orbital element because H is, see, all these orbital elements are somewhat visible. Okay? Is H visible? Is angular momentum visible? That is, in reality, is H visible? Is velocity visible? You cannot really measure velocity either, actually. You cannot measure velocity. You can measure acceleration, you can measure position, but you cannot measure velocity. See, everything you measure has to be, the measurement goes by Newton's laws. So if you, in fact, you measure force and relate that to acceleration. But you cannot measure velocity. This could be a trick question for some of you taking interviews. Can you measure velocity? So you should say you can never physically measure velocity. You can only derive. So how do you derive velocity from a measurement? What? Position over time, right. So if you measure position, if you measure your GPS position, you can get to at two instances of time, you'll get the velocity between those 2 points. The other way to do it is you measure acceleration and integrate it over time. Right? So any questions in this regard? 2% is a lot of points for one algorithm.